Welcome to the deep dive. For the last few sessions, we've spent a lot of time up in the clouds talking IP addresses, ports, all that logical stuff. Data just floating around conceptually.
But it's not really like that, is it? I mean, that data, those bits inside your computer, they have to become something physical to actually go anywhere.
Right, something tangible.
Exactly. Electricity shooting down a wire, pulses of light in a glass fiber, or, radio waves flying through the air, things you could almost touch.
Almost. So that's our focus today. We're leaving the logical layers behind for a bit. And we're diving deep right down to the base layer of the OSI model. Layer 1, the physical layer.
For a foundation.
Yeah, our mission is to really understand how those raw ones and zeros get turned into actual signals traveling across a medium, like the factory floor of the network.
It really is the foundation.
Yeah.
Layer 1 defines all the physical, electrical, mechanical stuff. Think of your network like a highway system. Layers 3 and 4, they're like the maps, the addresses, the traffic rules. Layer 1, that's the actual road, the asphalt, the concrete. If the road itself is broken...
Well, then nothing gets through. Doesn't matter how good your map is if there's a giant pothole.
Precisely. Right. A failure at Layer 1 means everything stops. Total communication breakdown. It's unforgiving.
But we need to dig into how those ones and zeros actually become... electrical pulses or light flashes.
Let's do it. And the best place to start is probably with the most common stuff. You'll find copper cables, particularly twisted pair.
Ah, yes, the workhorse. In pretty much every office, every home network.
Everywhere. Copper is dominant for local area networks, LANs, and there are basically two main types of twisted pair you need to know.
Okay.
First and most common is UTP. That stands for unshielded twisted pair.
That's your standard blue, gray, yellow Ethernet cable, right?
Yeah, exactly. It's cheap, it's flexible, does the job for most connections inside a building.
But it has that key limitation everyone bumps into eventually.
The distance limit. Absolutely critical. 100 meters. That's it. Try to run it further, and you're going to have a bad time. Signal just degrades too much.
Right. So type 1 is UTP. What's the other?
The other is STP, shielded twisted pair.
Shielded. So more protection.
Exactly. It has a metallic foil or braid shield wrapped around the pair, sometimes around the whole bundle, inside the outer jacket.
And why add that?
To fight off noise. Electromagnetic interference, or EMI. Think factories with heavy machinery, hospitals with sensitive equipment, places with a lot of electrical chatter. That shield helps keep the signal clean.
But distance-wise?
Same limit, still 100 meters. The shield helps with noise immunity, not really with distance.
Okay, so UTP and XTP. Now, something that always fascinated me about UTP, if it's unshielded, how does it work so well? Especially if you run it near power cables sometimes. It seems like it should be noisy. What's the deal with the twists?
The twists. That's the clever part. They aren't just random. Each pair of wires is twisted together at a specific rate. When external noise, like EMI, hits the cable, it induces a current in both wires of a pair.
Okay.
But because they're twisted, the noise hits each wire slightly differently over the length, essentially creating opposite noise signals within the pair.
And they cancel each other out.
Pretty much. It's called differential signaling and cancellation. A really elegant, simple way to build in noise rejection without needing that bulky shield. It's quite ingenious, really.
It really is. Before we leave copper entirely, maybe a quick word on coaxial cable. The thick, old-school one.
Yeah, good point. Coax. Think cable TV, older networks. It's definitely legacy for Ethernet, but you still see it for things like CCTV cameras sometimes.
Why? What's its advantage?
Mainly distance, historically. Thicknet coax could run 500 meters, much further than twisted pairs 100 meters. Less common now for data, but still out there.
Okay, so sticking with our main player, twisted pair. The twists handle noise, but getting the connections right is crucial. Let's talk pinouts.
Yes. This is where the physical meets the logical, you could say. Getting the pinout wrong means no connection. Simple as that.
Even with modern tech trying to help us out, you still got to know this. We need to know 3 main types based on how the wires, pins 1 through 8, line up in the connector. What's the most common one?
That would be the straight-through cable. This is your go-to for connecting different types of devices.
Like what?
Like a PC to a switch, or a router's LAN port to a switch. Pin 1 on one end connects directly to pin 1 on the other end, pin 2 to pin 2, and so on, straight through.
Makes sense. But networks are about sending and receiving, TX and RX. What happens if you connect 2 similar devices, say switch to switch, or maybe PC directly to PC, old school style.
Ah, right. If you use a straight-through cable there, you'd run into a problem.
Oh.
Both devices would try to transmit TX on the same wires, maybe pins 1 and 2.
And they'd both be listening RX on the same other pair, like pins 3 and 6.
Exactly. It's like two people trying to talk into the earpiece of their phones. Nothing gets through.
Silence, confusion, maybe some blinking lights if you're lucky.
Right. So for connecting like devices, you need to manually cross over the transmit and receive pairs. That's what a crossover cable does.
How does that work physically?
It swaps the pairs. Typically, pin 1, TX on device A, connects to pin 3, RX on device B, and pin 2, TX on device A, connects to pin 6, RX on device B, and the reverse happens for the other pair. Ensures transmit on one side, hits receive on the other.
Got it. Straight through for different devices, crossover for similar devices. What's the third type?
The third one is kind of special purpose, the rollover cable, sometimes called a console cable.
Ah, the light blue one, usually.
Often, yeah. Flat, ribbon-like sometimes. This one is specifically for connecting your computer's serial port or a USB to serial adapter nowadays to the console port on a router or a switch.
For configuration, right, when the network itself isn't up.
Exactly. Out-of-band management. All the pins are reversed end-to-end. Pin 1 goes to pin 8, pin 2 to pin 7, and so on. Completely rolled over.
Okay, straight through, crossover, rollover.
Hmm?
But, let's be honest, how many people actually carry a crossover cable these days? I haven't needed one in ages.
That's true. And the reason is a lifesaver called Auto-MDI-X.
Automatic, medium-dependent interface crossover. Rolls right off the tongue.
Huh, yeah. Basically, most modern network interfaces on switches, routers, PCs, they can automatically sense what kind of cable is connected and what device is on the other end.
And they just flip the pins internally if needed.
That's the idea. If you plug a straight-through cable between two switches that both support Auto-MDI-X, they'll figure it out and make the connection work as if you used a crossover. It's made life much simpler.
Definitely less fumbling in the bag for the other cable. But this feels important. Does that mean we can just forget about crossover cables entirely?
I wouldn't. For troubleshooting, absolutely not. Because sometimes Auto-MDI-X fails, or you're dealing with older gear, or maybe one side supports it and the other doesn't. If that link light doesn't come on between two switches, mentally you have to run through the checklist. Is the port enabled? Is the speed duplex okay? And is the cable type correct? Could I need a crossover here? Knowing the principle is still critical even if the tech usually handles it.
The knowledge has to be there before you can even diagnose the problem. Essential takeaway indeed. Okay, so copper gets us 100 meters. Twists help with noise. But what if 100 meters is nowhere near enough? Connecting buildings, cities.
Right. Then copper's limitations become really apparent. That's when we generally turn to a different medium altogether. Fiber optics.
Using light instead of electricity.
Exactly. We're sending data as pulses of light down thin strands of glass or sometimes plastic. The huge advantages. Immunity to electromagnetic interference light doesn't care about nearby power lines.
Makes sense.
And vastly increased distance and speed potential.
But just like with copper having UTP and STP, fiber isn't just fiber, is it? There are different kinds that behave very differently.
Correct. The two main categories you need to understand are single-mode fiber, SMF, and multi-mode fiber, MMF.
Single versus multi, what's the core difference? Pun intended, maybe.
It is the core, actually. Single-mode fiber has an incredibly tiny core, maybe 9 micrometers in diameter. That's thinner than a human hair.
Wow.
It uses a highly focused light source, typically a laser. Because the core is so narrow, the light pulse travels essentially in a straight line, a single path or mode, down the fiber.
And what does that single path get you?
Minimal signal dispersion. The light pulse stays tight and coherent over huge distances. That's why SMF is built for long haul. Think connections between cities, undersea cables, carrier backbones. Distances up to 40 kilometers or even much more are common.
40 kilometers?
Yeah.
Compared to 100 meters for copper. That's a massive difference.
Huge. Now, compare that to multimode fiber, MMF.
Okay.
MMF has a significantly larger core, usually 50 or 62.5 micrometers. Still small, but much bigger than single mode. It typically uses a less expensive light source, like an LED.
And the multimode part.
Because the core is wider, the light pulses enter at different angles and can bounce around inside the core, taking multiple paths or modes to reach the destination.
Ah, so not a single straight line. Like light bouncing down a hallway instead of going through a narrow pipe.
That's a decent analogy, but think about what happens if light takes different paths. Some paths are slightly longer than others.
So the light pulses arrive at the other end, spread out.
Yeah.
at slightly different times.
Exactly. That's called modal dispersion. The signal effectively smears out over distance, and that limits how far MMF can reliably carry data at high speeds.
So MMF is for shorter distances then.
Much shorter. Depending on the type of MMF and the speed, you're typically looking at distances up to maybe 550 meters, sometimes less for very high speeds like 10 GBps or more.
Okay, so under 600 meters, let's say, still better than copper's 100 meters, but nowhere near SMF's tens of kilometers.
Right. You use MMF within a building, across a campus, inside a data center, places where you need higher speeds than copper over moderate distances, but not the extreme reach of single mode.
So the key differentiator is really distance, driven by that core size and how the light travels. SMF for the long haul, MMF for the local area backbone.
That's the core takeaway, absolutely. Layer 1, physics dictating network architecture.
Okay, copper wires, glass fibers. What about no wires at all, the invisible medium?
Wireless. Yeah, most of us connect via Wi-Fi these days, at least some of the time. That uses radio waves.
So layer 1 here is radio frequencies traveling through the air.
Correct. And the two most common frequency bands we use for Wi-Fi are 2.4 gigahertz, cuz and 5 gigahertz. They have different characteristics.
What are the trade-offs?
Well, 2.4 gigahertz has been around longer. Its waves are longer, which means they travel farther and penetrate obstacles like walls and floors better.
So better range and coverage.
Right. But the downside is it's slower, offering less bandwidth. And that 2.4 gigahertz spectrum is crowded. Bluetooth devices, microwaves, cordless phones, neighboring Wi-Fi networks, they all use it. So more interference potential.
Okay, so better reach, but slower and potentially noisy. What about 5 gigahertz?
5 gigahertz uses shorter wavelengths. This allows it to carry much more data, leading to significantly faster speeds. Much less crowded spectrum too, generally.
Sounds great. What's the catch?
Range and penetration. Those shorter waves don't travel as far and get blocked much more easily by walls and objects.
So you need to be closer to the access point with fewer obstacles to get those high speeds.
Exactly. You use 5 gigahertz for performance-critical tasks like streaming high-def video or gaming, ideally when you're relatively close to the router. 2.4 gigahertz is better for general coverage throughout a house. Most modern routers offer both.
Got it. So we have copper, fiber, wireless.
Yeah.
How do we tie specific speeds to these physical media? That's where the standards come in, right?
Yes, the Ethernet standards. These define the rules for how fast data can move over a specific layer 1 medium, and thankfully the naming convention usually tells you what you need to know.
How does that work?
It generally follows a pattern. Speed base, medium type. Base just means baseband signaling. The speed is in megabits or gigabits per second, and the medium type tells you if it's copper or fiber.
Okay, give us some examples.
Sure, for copper you might see 1,000 base T.
Okay, 1,000 means?
1,000 megabits per second, or 1 gigabit per second, GBps. Base is baseband, and T stands for twisted pair copper.
And it still has the 100-meter limit.
Yes, that's implied for most base T standards. Another common one now is 10G base T.
So 10 gigabits per second over twisted pair. Needs better cable though, right? Like Cat6a.
Exactly. Needs Cat6a or better cabling to handle that speed over 100 meters.
What about fiber standards? How does the naming work there?
Similar structure, but the letters after base tell you more about the fiber type and distance. For instance, 1,000 base LX.
1 gigabit again. What's LX?
LX generally indicates long wavelength, typically using lasers. This tells you it's designed for single-mode fiber for those longer distances. Could be 5 kilometers, maybe 10 kilometers, depending on the optics.
So LX links to SMF and long distance. What about MMF?
For multimode, you'll often see SR or SX, like 10G base SR.
10 gigabits.
Short range. That immediately signals multi-mode fiber. The distance limit here might be around 300 meters, depending on the MMF type.
So the standard name encodes the speed, the general medium, and often clues about the specific type and range. Layer 1 physics turned into an acronym.
Pretty much. It's a shorthand for the capabilities.
And it's interesting, the source material pointed out how even in network simulators, like Packet Tracer, you still have to respect these Layer 1 rules. You can't just draw a line. You have to pick the right cable type.
That's right. The software enforces it. Try connecting a PC directly to a switch with a virtual crossover cable. It'll probably show a downlink or give an error.
Even though it's just software.
Exactly. You need to select straight through for PC to switch, crossover for switch to switch, or rely on virtual Auto-MDI-X, rollover for the console port connection. Those simulated link lights won't turn green unless Layer 1 is configured correctly, even virtually.
It really hammers home how fundamental this layer is. If the simulator needs to enforce it, you better believe it matters in the real world.
Absolutely.
So wrapping this up, layer 1 is really where the digital meets the physical, where the bits hit the copper or the glass or the airwaves. We've gone from the clever twists in copper cable fighting off noise
To lasers propelling data across continents in single-mode fiber.
and the trade-offs between 2.4 and 5 gigahertz radio waves for our Wi-Fi. It's all layer 1 engineering.
And if you take away just a couple of key things, remember those crucial distance differences. Single-mode fiber for the serious long haul, kilometers of it. Multi-mode fiber for connections within a building or campus, maybe up to half a kilometer.
And remember the why behind straight-through versus crossover cables connecting different versus similar devices by making sure transmit meets receive, even if Auto-MDI-X saves us most of the time.
That foundational knowledge is vital.
Which leads to a final thought. If setting up these physical connections correctly, choosing the right cable type, understanding pinouts is so critical that even network simulation software has to teach it and enforce it.
Yeah.
Then what kind of hidden problems, performance bottlenecks, or just weird, flaky issues are lurking in real-world networks? You know, that cable running between two offices or plugged into the back of a server. The one everyone just assumes is fine because, well, it's just a cable, it works. Right.
That's a really good question. How often do people actually check or even think about the quality and type of that physical link once it's installed? It makes you wonder what performance is being left on the table or what intermittent issue is caused by simply neglecting the details of the road the data travels on. Something to definitely think about next time you plug something in.